Добрый день, коллеги. Приветствую всех собравшихся.
Good afternoon, colleagues, and welcome. There will be several presentations from our Institute for System Programming of the Russian Academy of Sciences. Andrei Fedotov spoke before me. He talked about crash analysis, and we will follow up with our presentation. Again, we represent quite a big institution that began analyzing the code back in 1990s when we started our cooperation with major Western vendors. And now among our partners are domestic companies too. In terms of development of secure software, we promote a stack of solutions. They address the regulatory requirements, and they are very practical. They correspond to the needs of the developers. This stack is cost efficient and compliant. I'm happy to see that here at Off-Zone there are many discussions around fuzzing. This track hosted a series of presentations. Another track, they also offered several presentations. And I remember many years ago, Andrei Fedotov, the previous speaker, and several other guys, we were at a different conference, and the speaker was talking about fuzzing of Windows drivers. And he was saying that it's a promising technology, but it's quite dirty. You have to act quickly. But now, 10 years since, fuzzing is very high-tech, and people use it not only for their own pleasure, researching different bits of code, but they use it for production needs. Again, on this slide you can see my idea of the pipeline, how it should be structured so that everything matches, so that everything is integrated into a single workflow. Fuzzing doesn't answer the question of where I have a vulnerability. Fuzzing is a solution that generates crashes. And then you have to understand what interface you are testing. What is this interface? Is there any need to test it at all? Or maybe this interface is not part of the attack surface. Maybe it's best left to its own devices. So until recently, only experts could answer this question. We're all humans, we make mistakes, and even the best experts can't guarantee you the accuracy of a million line long code analysis. Crash analysis, crash triage can also be embedded into this workflow, and it can be automated. We'll talk about that. We'll also discuss the fuzzing engine and how to make it more efficient so that your server wouldn't just waste electricity, but would ensure excellent coverage. So, from the very beginning, you need to justify which interfaces and modules need to be fuzzed and how to calculate coverage, then execute the task efficiently, and then sort through crashes and decide which of them must be fixed, which of them are of the greatest priority, and which can be postponed. Now it's my pleasure to pass the floor to Vlad Stepanov, a colleague of mine, and he will explain how, using virtual machines and introspection, we can find the attack surface in large, complex systems that consist of a big number of components. And even in a situation when we do not have enough source code. Over to you. Hello, colleagues. Fuzzing is a cool technology. In practice, we first need to decide which interfaces must be tested and to which extent, because not all functions of the software libraries are used in an attack. And the decision in terms of the priority is based on the attack surface. Attack surface is a set of software system interfaces that are directly or indirectly available for external influences. At the moment, determining the attack surface is a manual job which is performed by an expert. An attack surface would include files, processes, sockets, scripts, loadable modules, and functions related to data handlers if the data comes from untrusted sources. Based on the above, we devised a technique of automating the attack surface detection. We use dynamic triaging. Then we taint or label the incoming data if the data comes from the outside, and then we trace the response of the system to this tainted data. Because we use a system emulator, a full system emulator, we can detect tainted data in all processes and in the operating system. By using introspection mechanisms, we can trace the modules and functions that processed the tainted data from untrusted sources. As a result, we can decide which modules and functions should be tested to understand how well they are protected from malicious influence. Eventually, we'll be able to cut down the development and certification costs. And at the same time, we'll be able to improve security of software by eliminating human error in determining the attack surface. Besides, in addition to the technique of tainted data and virtual machine introspection, we also use the deterministic replay technique. All of this allows us to develop the Snatch tool for automatic attack surface detecting and Snatch to visualize it. Now, let's discuss these technologies in greater detail. Virtual machine introspection. It provides us with information on the guest system. On the virtual machine, there are two approaches to introspection: ABI-based approach, the interface-based approach. The idea here is that we would capture system calls. We will process input arguments, and also in the memory we'll find program modules and we'll pass the headers. Since the binary interface doesn't change often, one implementation of such an approach can cover a whole family of operating systems, but this approach has its limitations. For instance, sometimes it's difficult to determine the names of the processes and full names of the files. Therefore, we need a different approach, and the second approach is based on kernel-based approach. We use the kernel structures parser. This approach provides more information. However, it is associated with a different problem. We need to know the offsets of the fields and data structures. In Linux, the structure data offsets differ depending on the kernel version, depending on the build, and also they can be randomized during every recalculation of the kernel. Both approaches to introspection are adopted by our solution. The offset, in our terminology, is known as profile, the introspection profile. So the idea is to generate the introspection profile for the operating system in question. The available solutions require either symbols or open or source code of the kernel, like Panda, for instance, embeds a special agent into the guest system that collects the data. We do not use agents. Instead, we analyze the running processes of the operating system with special stylistic algorithms that compute these offsets. This is the heuristics example. We start the file, we retrieve the name of the file, then we brute force the data structure offsets so that from the tables, from the spreadsheets of the virtual machines, the guest machine, same file name could be retrieved, and the offset identified will be included into the profile. This is how we parse the files and memory views. The VMI technique is combined with labeling, data labeling, or data tainting. We can visualize the flow of the data, tainted data, as a graph. How do you build such a graph? First, we use introspection in order to determine the processes, interactions, whether the files are transferred via files or sockets or shared memory. If this is not enough, per every byte of guest memory, 2 bytes of shadow memory would be allocated, and the shadow memory will store data about the data that's written into the guest data. When a different process reads the data, we can trace interactions. And now let me describe the algorithm of using our tools. First thing is you prepare the virtual machine and the target software. Then you record the target software execution scenario in the virtual machine. Then you choose some input data for labeling or tainted. Could be files or network connections. Then we replay the scenario and we save the attack surface. Then the saved attack surface is loaded into Snatch, the visualization tool, and then we explore the attack surface with interactive reports in the browser. And this is how the output would look like. Here is an example. It's a Taranto memory database server application. In our scenario, the server requests a query from the user, and these queries are all tracked. You can see here a graph showing you the interaction between processes. After that, we open the process tree. Now we see all the processes recorded in the system. The pink is used to highlight the kernel associated processes, and red and blue is used to identify processes that interacted with the tainted data. We can see here 2 processes called Taranto tool, but initiation command differs. Then we can review the process timeline. We will learn when the processes were created and when they were finalized. In resources and traffic, we'll see files and sockets with which the processes interacted. And if necessary, we'll be able to view which data was written and was read. And we can also see the network traffic. We can open it and research it in Wireshark. Call graph probably is the most interesting aspect of the whole software. Here you can find the fuzzing targets. The blue color is used to identify tainted data. In practice, however, probably will not be able to understand the context in which these functions are executed and how critical they are. Then you can go to the flame graph to understand what was happening. While we were replaying our scenario, you'll see which functions were performed, how long it took them to be executed. And these trees and flame graphs are built both for the system and for the kernel of the system. We can see here that those functions that process HTTP queries were highlighted, and here you can see the JSON format functions. One other feature of our analysis of tainted data is that our taints are associated with a 1 byte value. When the data is tainted, its value is 255. When the data is propagated, when the data interacts, then the value will be offset by 1. When we generate the attack surface, we will set the threshold values for these labels. If the threshold value is 255, then we will see as labeled as tainted or tracked only those functions that did not change through interactions. But if the threshold value is lowered, then we will see more functions. We will see other functions that will handle some derivatives of the original data. In conclusion, just wanted to mention that in addition to the above-mentioned possibilities, our tool has other features like creating a list of Python scripts, or determining the processes running in Docker containers, and also building call stacks for Python functions that process tainted data. Now the floor will go to Alexey Vishnyakov, who is my colleague. Great, thank you. Hi everyone. Let's go back to fuzzing. So here's what we do for hybrid fuzzing and dynamic analysis. Our product is called SIDR. You can use SIDR to build dynamic analysis processes for secure development. SIDR, in fact, is not just a set of those tools. It has always been a dynamic symbolic execution tool that uses Triton for symbolic execution and Dynamo Rio for concrete execution. SIDR finds new paths and enables error detection. SIDR Fuzz includes SIDR. It launches SIDR together with popular fuzzes like libfuzzer or AFL++. And the symbolic execution generates additional input data, and fuzzers can explore how to reach paths. SIDR Fuzz supports multiple programming programming languages, including C, C++, Rust, Go. It supports symbolic execution, and we also added Python and Java for ease of use, so that you can use them without symbolic execution. What is symbolic execution, by the way? Dynamic symbolic execution means that we analyze one path, we launch some input data, the software receives the data from a file, every input byte of the program will be marked as a symbolic variable, and all computations are based on SMT formulas. Symbolic states maps registers and memory to SMT formulas, and we built a path predicate that would contain the constraints on the path along which the program was executed. After that, what we can do is we can go in a different direction to expand our coverage, or we can set up some specialized checks to detect special errors, like out of bounds or integer overflow. Over here you can see a Sidra architecture schematic. You will notice that it's split into two processes. Here we've got two executors, a concrete executor and a systemic executor. We use DynamoRio for a concrete execution. If you reload the code, it will either work very poorly or it will just go down. So we decided to separate this heavy load payload into a separate process, and in dynamic execution, all the light-weighted processes take place, like discovering input data, like reading from the file, and we send all instructions register and memory values are then sent to the symbolic executor, which performs symbolic interpretation. Instructions are interpreted using the Triton engine. Triton builds the path predicate, security predicate is built, and then from the predicate path, irrelevant constraints are removed that don't have any impact on the execution path, and then Bitwusla resolver selects new input data that will be taken via a new path or will activate a defect. How do you use Sidra Fuzz? We were inspired by Docker. We wanted to make sure that Sidra Fuzz would know the path towards config. And we also introduced notion of a project. Projects are artifacts, post-fuzzing artifacts that are generated that could be useful in one directory. The corpus, the crashes, some working directories of the fuzzer, the cluster, crash clusters. The speaker before me talked to about cluster symbolic checkers, coverage, etc. logs, and over here you see the toml config file. You see the lines to initiate the target for the fuzzer, and with a view to the coverage. And also there are some additional arguments of the fuzzer. Why do we have two binaries here, for Sidra and for the fuzzer? Well, we need them because basically if the program is built with sanitizers, which we do for fuzzing, if you launch it via DynamoRio, they will use the same address space and it will fail. But even if this technical constraint could be overcome, it would still overload the symbolic execution with extra instructions that needed interpretation. It would complicate the resolving of predicates. You can also indicate the number of epics of symbolic execution, fuzzing, During the first presentation, the speaker said that you can, if you change the schedule, you make changes to the schedule, you can find new bugs. But actually, in documentation, you can read that it's recommended to regularly change the parameters of the L++ schedule. So basically, all these parameters will be automatically generated. Various L++ processes will be launched with different schedulers and options. You can't develop fuzzes and not benchmark them. It's important to know where you stand versus other fuzzes. And there are many. As you know, we published this paper where we compared Cedar Fuzz with several other open source code fuzzes. The full results can be found at the link at the bottom of the slide. We managed to achieve higher coverage than other fuzzes. And we also did better than many other fuzzes with most benchmarks. This is a Google benchmark, FuzzBench. It's a recognized benchmark, and it measures coverage per unit of time. And it also launches the same fuzz several times. It's important when you measure the performance of the fuzzers, you start them twice. You get different results, you get different metrics. So it's important to average the results across several runs. The thick dotted line is the median result for coverage. Over here you can see the Cedar and lib fuzzer versus two lib fuzzers. Then, and again, every time we're showing Cedar in green and other fuzzers in blue. SymQMU is shown here, and Fuzolic, right bottom corner, Cedar is shown here in green. Again, you can see here that these fuzzers are pretty close. Fuzzers today, they compete like in a race, or sports car race, when they are competing over some percentage points. We forked OSS Fuzz, Google's OSS Fuzz, for hybrid fuzzing. I wanted to support hybrid fuzzing because, like I said, same fuzz targets. Sometimes you have to modify the wrapper to make life easier for the symbolic execution. We added more than 65 projects, about 500 fuzz targets. In about 18 months, we discovered more than 135 new errors in more than 25 open code projects. TensorFlow, PyTorch, Torch Vision, Cairo, OpenJPEG, Poplar, Unicode, Tarantul. We researched Tarantul. All trophies are published on GitHub, so I'll refer you to GitHub. It's also a useful repository if you want to fuzz something. Maybe you'll find your open source project there. Or you can do the same with OSS Fuzz. You can do the search in OSS Fuzz. And we also found more than 20 issues with symbolic checkers. Those are the additional restrictions that can help you look for specific errors post-fuzzing. We use dynamic analysis pipeline. Step 1, we start hybrid fuzzing with Cedar and the fuzzer or FL++. We prune the corpus, we identify the errors, we collect coverage, and then we triage and we upload to new repository Factorio. This is how our CI integration looks like. We use the GitLab.
докер-файлы с описанием
all the Docker files,
окружения подфазинга того, как собирать
configs.
обертки. Есть какой-то внешний триггер
We have
события, по
an
которому запускается
external
фазинг.
trigger event that starts the fuzzer. So first we collect the Docker image with all the wrappers and everything, and then as for every image, a dynamic analysis pipeline is launched. And as a result, various fuzzing artifacts are generated, and the corpus will be cycled. It will be accumulating over several runs. And we'll also have crashes in a defect dojo. That's what we did. We integrated with Leave Fuzzer. They have a shared directory to which all the fuzzers are writing. The seeder takes files into this from this directory and adds new ones to this directory, and this is where we find out which files seeder found to be useful. It's also important to select inputs. We are interested in having smaller inputs, but the ones that enable new discoveries. We minimize our corpus. In terms of automatic generation of parameters, if you want to have correct fuzzing, I spoke about that already. Schedulers and everything. Symbolic checkers. Symbolic checkers detect various errors. More equations are added, and they run. The fuzzer runs on a pruned corpus. The generated seeds are verified on sanitizers to check for false positives. And crash lines, we use crash lines to duplicate errors. This is what symbolic checkers find post-fuzzing. For instance, these developers use OpenJPEG, and they wrote in one of their blogs that it can't overflow, but it can. You see, they found an integer overflow possibility, and then we run the same with sanitizers, and we get a confirmation of this error in a different line. Here's another example of errors of integer overflow that results to buffer overflow. So basically, we've got this multiplication of a variable symbol count by 2 by size of, and then symbol size will overflow. There will be fewer symbols than are required to store the whole array, and as a result we go out of bounds of the array because it will be indexed along a regular index which is under out of bounds. Cursor, you know all about it already. We need to thank the previous speaker. Please rate us at GitHub. The reports are collected from sanitizers, then they are deduplicated and clusterized. Additional reports are generated with cluster GDB, because sometimes we need to understand that the sanitizers are not crashing with the seeds, or sometimes the sanitizers crash first, and then something even more terrible happens. And then we also analyze all kinds of errors. So basically, all of this is uploaded in Dojo. You saw this already in the previous presentation. This is the cluster report. You can see severity of the crashes and the type of crash, like overflow, buffer overflow, and the line where it happened. And then you see the same in Defect Dojo, and you can analyze the reports there. Thank you very much for your attention. We have Telegram channels, so please follow us. You can send your questions there. Fuzz also has a website, and you can read more about it. And we'll be happy to answer your questions. Thank you very much for the presentation. When you spoke about Natch, you mentioned that it's necessary to understand the field offsets in the kernel, but as far as I understood, it's a user space tool. Can you provide an explanation? We need offsets for introspection. There are user processes. We need to understand how they interact, which files they read, which files they write, how they exchange data through memory, and we need to analyze not only what the apps are doing themselves, but we also need to understand which kernel structures are involved through system calls in the process. But theoretically, is it possible to have a similar tool for the kernel itself, like a standalone kernel tool? Well, it depends on what you want to achieve. Well, I would like to see which kernel functions are involved in system calls with such and such arguments. Yeah, that's exactly how it works. That's what we do. You can view the codes of the kernel, the functions of the kernel, and you will see which ones are associated with the tainted data. So it works like that? Yes, yeah. You will be able to see all the kernel functions and the tainted data. Oh, wonderful. And another question is a bit of a philosophical nature, but this labeled or tainted data analysis, is it any different from the fuzzing with coverage? So I start fuzzing, I get some coverage. If I fuzz just the interfaces that are my targets, then basically I analyze the tainted data, or is my understanding wrong? Well, with your permission, let me join this discussion, since I was more involved with this part of the project. You are not interested in seeing all data when you run fuzzing. You fuzz the, say, network interface, and you are interested not in all of the interface, but you're interested in the payload, which is associated with something nested. And tainted data analysis allows you to specify to a specific byte things that you're interested in. General fuzzing will tell you, more general data. You fuzz something, you fuzz some service functions that would work on their own and that are not in any way related or interact with seeds or input data. And when you process the external data, well, you have to separate them. You have to individualize them so that you will be able to target the functions of the program in which you are really interested, because this is a systemic thing. As Vlad was explaining, one thing is attached to the other. I mean, you identify parts and bits that you're interested in. At the same time, you see everything that happens in the system, your software and the environment in which your software is functioning. Okay, but why would I be interested in some body of data? I'm looking for secrets and I need to know whether they leaked. Well, no, not necessarily. You may have some deep encapsulation on the protocols, and you are not interested in seeing everything that's below, some transport layer. Oh, wonderful. Got it. My last question is on the last part of the presentation. You mentioned that when classifying crashes, you can understand or see whether there is something more critical beyond that crash or underneath the crash. Oh, I understand. So you get an alert from sanitizers, and then you collect this data, but you do not use sanitizers anymore. You use GDB, and you fuzz with GDB to understand where crash is going. Sometimes sanitizers capture an overflow kucha, but some more critical error will be hidden or will be concealed with the crashes that were detected. Okay, with symbolic execution, you disable sanitizers, but symbolic execution did not reveal the bug. So maybe you need to use sanitizers twice. The first, do you know what I mean? No, not really. So in the first run, you use sanitizers, and sanitizers produce crashes. But this crash hides another crash, a more serious one. So maybe symbolic execution, the second crash. No, I'll give you an example. Better. A sanitizer shows you a warning. Oh, there. User free read. But in fact, there is a user rewrite behind it. Well, symbolic will be able to find this deep down bug, and you can verify it with sanitizers. So there is a strong check when the lines match, right? But there is a weak check. We found a new bug which was not revealed during the initial run. But this will also be classified as a warning. So you run sanitizer several times. Yes, customer GDB will see that terrible thing, critical thing the next time. Oh, this is amazing. Yeah, well, it will be a new one, even if it's not a very serious one, but it will be a new match, and that's why it will be recorded and added to the storage. Hi, thank you very much for your presentation, and I have two quick questions. You said you forked OSS Fuzz, and you did your own Cedar OSS Fuzz. So you forked together with the infrastructure? You use, you do it where? It's just the business, it's just the code of the Dockers. We modify the code of the Dockers to collect binary. Sometimes you have to modify the wrappers yourself, too. But then we got lazy, and we started adding Fuzz targets not via OSS Fuzz, but directly. Maybe it's not a good thing, because sometimes you need to share this information. But in the Fuzz, we have our own infrastructure. It's not their infrastructure. Cedar Fuzz is a tool for automatic integration into CI, basically. The dynamic analysis pipelines can be called from CI, and they will perform typical tasks during fuzzing. In the similar fashion, well, ours is close to cluster fuzz, but we have our own development. We have a Docker builder, and in this Docker, in the project, we will start the dynamic analysis pipeline with the fuzzing and crash analysis and uploading. So it's your infrastructure. Yes, it's our infrastructure. Well, an outsider take your code and set up this infrastructure? Yes, sure. All the commands are shown here. There are 5 of them. That's the code. It's that simple? Yes, it's that simple. Okay, one last question. You had slides where you compared performance with other symbolic executors. When adding to the pipeline, when adding your Cedar to the pipeline, did you compare whether performance changed, or rather, how much more memory and infrastructure and performance is required to fuzz some product adequately? Well, today symbolic executors require twice as much memory as a fuzzer, but we worked with it. It was different at first. In the beginning, it could consume a whole 100 gigs, but we set limits on resolving formulas, building formulas, memory. We have memory limits at different stages of the Cedar workflow, so that's why it's scalable. But in a CI system, usually we start 3 fuzzes and 1 symbolic executor for 1 fuzz target. And symbolic executors, are they privileged containers or no? No, not necessarily. Excellent. Hi. My question is, how much time does one test case with symbolic executor take? And the second question is, what was your question? Okay, the first question. Let's start with the first question first. Well, the answer to your first question is it depends. It depends not on the size of the program, but on the number of instructions that you will taint. It's a variable, varying number. There are some fast targets like XML. It can take a couple of seconds. Fast targets such as Poplar PDF parser, it will take 20 minutes. Oh, so it means you do not symbolize everything. No. There are techniques. If you're interested, on the website, you can find a lot of academic publications on symbolic executors. We interpret only symbolic instructions. Everything else is concrete because our approach is dynamic. We take real values from Dynamo Real. We don't need to simulate them symbolically. Okay, the second question is, so you did this benchmarking versus libfuzz and stuff, but if you add some custom mutators that know about the protocol over which the test cases communicate, it would be interesting to see whether your product is more efficient or less efficient. It's a good topic for a joint publication. Well, of course, the performance will go down. Symbolic, the idea of symbolic, it helps you when you don't know the format very well. If it's a bad corpus, symbolic is going to interpret everything. It will start understanding the format. If you know the format very well, then the profile will not be very high. I don't remember, and maybe we had this somewhere. Okay, never mind. We benchmarked the Rantel. I think they use Protokov in the Europers. It means that they know the format that they fuzz, but Cedar adds its contribution, its might. Yes, but there are some interesting cases, even if we know the formats in and out, even if we have a mutator fit for the format. There is still some space for implementation. Implementation can take, like JPEG, libtool, or JPEG something else. They are different. And here, symbolic executors may be of benefit. It would be interesting to see whether it's going to make any new discoveries. Okay, by way of a general comment, fuzzers, better fuzzers, advanced fuzzers can help you fuzz from scratch if you know nothing. But harness and corpus are the basics. The better are your targets, the better is your corpus, the higher is the performance of your fuzzer. Corpus and harness and manual work can sometimes, it can prevail over any fuzzer.